Now let's try to understand why this data alignment requirement comes in the first place. Why we need to store half word as an even address, word as at an address which is divisible by 4, and yeah, byte we can store anywhere, and so on and so forth. So let's try to understand this part. So we have in our computing system, we have two things, right? One is the MIPS or a processor, right? And a memory. They are interacting. Now from MIPS perspective, a memory is a device which is byte addressable, means each address points to a byte. Okay, so 32-bit address, so we have like total 4 gigabyte of memory space. Now memory as an electronic device, it's always word addressable. One read gives you one complete word. Now we are using one like word addressable 4 gigabyte memory, but MIPS is thinking whatever it is memory it is interacting, it is byte addressable 4 gigabyte memory. Okay, so that means your MIPS is issuing 32-bit as an address. Okay, but out of the 32-bit, higher 30-bit is coming to the memory as an address, because memory as an word addressable 4 gigabyte space means each address is 4 byte each address. That means it needs 30 bit of addresses to point to 32 bit of address to point to any 4 byte container, right? Any 4 byte container. So that means it needs a 30 bit as an address. Then what happens, let's say it is accessing, let's say the first row, the row at memory address of the device. Here in the memory address means address of the device, not the address issued by the MIPS processor. This is your the first lower byte goes into the lower byte of the memory that processor is looking out for. Okay, so this is kind of like so this is like a conceptual space I'm talking about. This right hand side is a physical memory which is giving 32 bit for a reading any point of time, and these 32 bit are basically filled out in successive 4 address location as far as the processor is concerned. This is the processor view, right? Your LSB goes into your lower address, MS most significant byte of that whole word coming from the memory is placed into the higher address. Okay, so lower bit lower, higher bit are higher. So this is again like a little Indian system we are talking of from Indianness perspective. Now the point is here we are issuing, MIPS is issuing 32-bit address. Out of this 32-bit, first and second bit are dropped, and rest bit number 2 to 31 is presented to the memory as a device, and on that address it returns like 4 byte, and these 4 bytes are placed from lower address to higher address as from lower byte to the higher byte. Okay, that's how the whole system works. That means when I'm receiving a data, 32-bit data, like through various load operation like load word, load byte, load half word, all of this load operation, this memory as a device will send out 32-bit data. Okay, it doesn't care, like it doesn't know anything about load word or load half word or load byte. It just know read write request upon certain address. So you are placing a 30-bit address and you are requesting and read to this memory. So what it does, it all does is just get the 4 byte from the memory and send it back to the whoever is like requesting, like connected electronically. So then if it is a load byte or stored byte, let's say it's a bidirectional, it's the same concept. For the load byte, if it is an higher address request, like let's say 003, the higher byte will be picked up. Like this is the most significant bit has been picked up for an address 3. Okay, address 3 is this guy. For address 2, the other half, bit 23 to 16, will be picked up as my data, incoming data by the MIPS processor. And then if the issued address was a 1, then 8 to 15, that bit will be picked up for the MIPS processor. And if it is 0, address 0, then lowest LSB side, lowest significant byte would be picked up from the MIPS processor. And then if it is like a load half word kind of thing and on an even address boundary, we are not yet talking about why it has to be even or why it has to be like divisible by 4. If it is an even address, let's assume it. So if it is an even address of 2, then we picked up the higher half word of the whole 4 byte. And if it is 0, load half word, then it will be the lower half word of the entire word, that loader. And load word is like, okay, 0, it just all 32 bits are placed into this order, like from 0 to 3, it will just all those bytes will be placed like from a conceptual ground from the MIPS perspective. So this is how this load word, half word, load byte, like different data size reading and writing happens in the real world with the real memory system. Now this arrangement poses a challenge here. Okay, let's look at the half word alignment in the memory. So let's say I am accessing even address, okay, which is like this lower 2 word, fine, or higher even address, which is like this is like for accessing 0 address 0, and B configuration is for address 2. Okay, I can access the higher 2 byte because this whole 4 byte is returned from the memory. Now if the address is 3, then what will happen, I need to like access the MSB, most significant byte of that address, and LSB of the next address of the memory, like as a memory device, like not that address that issued by the MIPS, but as a memory device address, you have to access this address, the issued address at the MSB, and your LSB of the other like address plus 1 for the memory. Okay, not from the MIPS perspective, just device perspective. That means at least for the address 3, if I need to do a half word read, I have to access memory twice for this address and next higher address of the memory device, right? So 2 read is involved, and then we need to concatenate, need to take LSB of the higher address and MSB of the lower address and do that. And the other case, when I'm trying to access a lower half, like address 1, load half word at address 1, then my 2 bytes would be these red boxes, right? These 2 bytes, red bytes as marked as red, I need to access them. So this doesn't involve an extra memory, that's okay, but it involves in complexity in data extraction circuit. Right? This is not a straightforward circuit we are talking of, as it seems like that, hey, first of all, I need to distinguish between, okay, if it is within that one memory read boundary, I'll return it, I'll use it. If it is not, then I'll throw an exception. Like I can, that means I'm allowing 1 but not 3. I am allowing 5, not 7. Something like that, right? In the half word address space. Like so, if I would ever allow a D in the system, then my allowed address for the half word would be 0, 1, 2, not 3, right? And then 4, 5, 6, but not 7. So this kind of lost uniformity, we cannot just make a rule like that on the hardware circuitry. But on the other hand, other assumption that I can only access the even address, means 0 or 2, but not the odd address, that has kind of generalized rule, generalized notion of the rule, which if it is much generalized, easier is the circuit. If it is less generalized, it's a complex in the circuit. That's one way to think of this. Okay, there are other complexity involved too. So we discard those C and D conditions, like any odd address we're trying to access are not permitted. We only access half word at even address boundary. Either it has to be 0 or 2 or 4 or 6 or 8 and so on and so forth. Any even address we can do that, because we can just access one memory and either access the lower 16-bit or upper 16-bit from it, depending on what address I am asking for. Similar logic, similar understanding can be applied to the lower word alignment in the memory as well. So one whole word, which is 4 byte, which is okay, right? It issues a word, issues a address which is like divisible by 4, and among that, first 2-bit is dropped. So that means theoretically you are left shifting by 2-bit, right? Right shifting by 2-bit. First 2 bits is dropped, mean like you are constructing a 30-bit value, which is by right shifting the 32-bit to make it a 30-bit values, right, for the memory device address, which is essentially divided by 4, right? And that address is read up. Now anything other than that, any address other than divisible by 4, completely divisible by 4, will need 2 memory access, because that word will cross the device address boundary. Okay, so let's say you are doing a load word of address 1, right? So this is load word, configuration A is load word of address 0, right? So that 0 address has been read and all the 4 byte is used as a word. Now load word as 1, what does it mean? So from this row 3 byte, and next address, which is address 1 of the memory device, and pick up the LSB, right? Same for like load word from an address 2, again it is crossing the memory device address boundary, where we need the 2 memory read in that case. Similarly for the D. So we abandon B, C and D, accessing that possibility. We said that, hey, we will access only an address which is divisible by 4, because we can derive, and like that address, anything divisible by 4, we can derive that address by directly shifting 2-bit of this 32-bit address to make a 30-bit address for the memory device, and we will stick to that. So that's the reason why a word can only be accessed from a memory location which is divisible by 4.